Hi everyone, welcome back to the workshop, and it's repair time again, and this time I've got a Fluke 43B power quality analyzer. Bought this one online and apparently it was working perfectly for a couple of years and then just completely died, wouldn't switch on one day. Now what the Fluke 43B is, it's a power quality analyzer. It's all about measuring power. It's a battery operated device and you would take it out onto site or inside equipment, that sort of thing, to measure voltage, current or frequency problems on the power side of things, single phase and three phase, where you might be looking at harmonics, sags and swells in voltage, etc., transients, inrush currents, and it's got the ability to log data for up to 16 hours. So it's faulty, it's dead apparently, so we're going to try and effect a repair. Now, as I said, it is battery powered, but it does actually come with a AC adapter here, a Fluke branded one, and this is obviously for charging the battery inside the unit, and it's just all taped up here, and it looks like we've got an adapter here that plugs in the top to give it a BNC connection. Now there is a load of accessories and a carry case to carry all available for these units, a lot of accessories. Unfortunately, I don't have anything apart from this one adapter, but I don't think I'll need it for what I want to use it for. So I've got no idea whether it's AC adapter that's at fault or whether there's a battery problem or something more sinister wrong inside the actual unit. One thing I do notice is that this long connector here that plugs in the side here for the battery charger, it possibly is broken and it's all been taped up there. So we'll have to have a look at that, and maybe that's the problem, who knows. So I think the first thing I'm going to do is actually to check the AC adapter here, the charger. Is it possible that charger's faulty and it's just a completely flat battery? Who knows, but we'll have a look at this first. Well, first things first, let's get this sellotape off of here. And the cable looks otherwise intact really, as do the pins and where it enters the body of the charger itself. I think I'll take a look at this here before I actually switch on power. So let me just remove this tape and let's take a look underneath here. Yes, and I think I can see what's gone wrong here. Let me try and zoom in and see if you can see that. So it looks to me like this strain relief, something's gone wrong underneath there. I can rotate that far too easily. You can see this actual outer covering here doesn't go all the way down inside there like you'd expect it to. I can see a red wire down in through there, and that's one of the cores of the actual cable itself. So it looks like this outer cover for the cable is actually pulled out from inside that connector there, and hopefully it's not pulled it off of the pins inside. The only way to check that is, I'm not going to put power into it. Let's open up the adapter and take a look inside and do a continuity test from one end of the cable right through the other. And it's a very simple design, just a transformer, bridge rectifier and a large bulk cap there. But the cable at this end looks to be okay. I will lift out the PCB just to make sure there's no broken solder joints on the underside of that PCB. So it should just lift out, I think. Yep, there we go. Yeah, and all those solder joints just look perfect. So I don't think there's any problem at this end. And the connections down on the plug there are just via these spring contacts here, which just go onto these pads in the PCB there. A little bit of arcing, but not too much. Well, quick test later with the multimeter, and the cable's actually intact. It's certainly not shorted out at this end, and its continuity end to end is fine. And it's well soldered on at this end here, so I don't think there's any problem with the power supply. The only thing I don't like is having the strain relief not really doing its job. It's not really got the outer plastic of the cable down inside the strain relief. But I think we can fix that. So how can we get this back down over that red and white wire down as far as it will go? So basically the answer is just grab the cable in one hand and just do this with the cable and just push that outer covering over the top across the inner cores, and it will feed itself back down into the strain relief. And I can already see it's working because there's a little mark in the cable there, and that's starting to disappear in underneath that strain relief. And the idea is take it as close to the power supply as you can. You don't need to use too much force on this length of cable because there's a lot that can move. So we'll just do that from end to end there. And let me zoom in, have a look at the progress. I don't know if you can see that, but the red cable now starts about here, so I've already moved it about a centimetre. So I'll just keep on doing that until that red wire inside there basically disappears. Yeah, we're just over halfway. I think that's as far as I'm going to get it. So what actually causes the outer cabling to move, the inner cores to shift around inside the length of that cable? Well, actually, it can be caused by coiling the cable too much. I mean, you've got the power supply here, and what people often do is just wrap the cable around it like that. Well, every time you bend it by that sort of radius, you are shifting the inner core very slightly. Now, in a good cable, it won't shift by much, and it'll shift back again when you straighten it up. But with a cable like this, it's obviously shifted, not moved back, and every time it's done it, it's shifted that little bit until the point where almost those inner cores are appearing outside the strain relief there. So before I put it back together, I'll just double check that the connections are still okay, that we haven't broken any wires, and I'll put the power supply back together again and we can power it up and give it a test. Okay, and we're ready for a power up. So just have a look at the power supply here. It's 15 volt at 300 milliamps. And of course it's unregulated, so I've got no doubt off load it's going to be a bit more than that. So let me plug it in and let's see what we've got. Okay, here we go. Now it's positive to the outside. And let's just check, see what that is. And yep, we're getting 20 volts DC. Looks good to me. Okay, onto the main unit itself. So I've just hit the power button here. It's just doing absolutely nothing. No sign of life at all, whether holding it down or a single press. So I've still got the power supply plugged in, so let's plug that in and see what happens. So it goes on the side here. And that's it plugged in. Of course, there's no indication of any charging or anything. And again, it just seems dead. So I'm actually going to leave it for a few minutes just in case the batteries are absolutely totally flat. And we'll just see if it actually comes back to life with just a few minutes of charging. Well, no luck leaving it on charge. Let's open it up. And there we go, we're inside the unit. Let's check it out. Well, first things first, here's the battery, and it looks like it's the original Fluke battery. No idea what sort of state it's in. It's a metal hydride battery, so we'll check that out, and hopefully it's good and we don't have to replace it. So here we are inside the unit, and the first thing it strikes me, it's really clean, which is a good sign. Taking a look at the circuit itself, right in the middle there, and you can't miss it, the Fluke branded Spider it's called, and it is a large digital ASIC. It's used for all the digital I/O around the device. Down in the corner here we've got another ASIC actually, and that's for handling all the power side. Over here we've got two fast ADCs, two 8-bit ADCs. Looks to be a controller for those ADCs in the middle there, and a RAM IC down here. Over here, well, looks like we've got a small transformer, and that's probably going to be for the backlighting. Down here you can see those two white wires here that disappear under the chassis there. That'll be going off to the I presume it's a CCFL tube for the backlighting. Of course, you've got all these decoupling caps here, and which looks to be another transformer possibly, or a choke on that power side. And over here we've got the charge socket there, and you've got a bunch of other power related components. And down here you've got looks to be two LEDs. Actually, that's the optical interface which is on the side of the unit here. So you obviously got a receiver and a transmitter there. Over here we've got the two input channels required for the device, a couple of relays, and I think that's a couple of small ASICs there as well. Looks like they've gone to town with the use of ASICs on this board. You've got some protection circuitry around those inputs and another relay in the corner there. Now I do actually have the schematics for the unit, so we should be able to plug in the battery, plug in the external DC adapter here, and actually see if we've got any power anywhere on the board. Hopefully we don't have any fundamental problems like a knackered ASIC or anything like that. So let's take a look at the schematic. Let's see if we can understand the battery circuit and the external DC input circuit. Let's see if we can understand how it charges the battery and also powers the device. And so here we are, we've got the battery over here with its internal temperature sensor, etc. And we've got the power adapter socket down here. So starting down here, you've got a common mode choke filter arrangement here. You've got a Schottky diode there, that'll be for reverse polarity connection. And immediately goes through a current sense resistor and away off to the charge circuit up here. The voltage across the current sense resistor is detected by the ASIC, so it can detect whether we're plugged in or not to decide whether it's going to actually enable charging of the battery. And that's done by this signal here, CHA gate, that controls this MOSFET here, obviously to allow dynamic charging of the battery. The battery connection itself, you've got 2 or 3 chokes, and you've got a detection circuit here for measuring the temperature at the battery. It comes straight into the ASIC there via those 2 resistors, etc. And this line here is the actual VBAT. This is the actual battery voltage itself. So there's a number of things we can check here. We can obviously check that the power is actually coming in to the charge circuit and up onto the battery, and of course we can check the battery voltage itself. So let's hook it up and see what we've got. So the first thing I'm going to look at is TP501 here with the DC adapter connected, and let's see if we're getting some sort of unregulated DC from that barrel jack there. And I'm also going to check VBAT here on TP504. Let's see if we're getting a battery voltage, and I should be able to disconnect the power adapter and then reconnect it again, and I should see some variance at VBAT with the battery connected obviously as the charger is disconnected and reconnected. So let's check that now. This is that first test point, and you can see I'm getting 16.1 volts. That's obviously coming from the barrel jack. And right next to it is actually the other test point for VBAT. And you can see that's sitting at 6 volts. Now it's a 4.8 volt battery, so 6 volts for charging is probably round about right. And if I disconnect it, hopefully we should see it drop slightly. And yep, it's going down to 5.6 and it's slowly dropping at that. Like I said, I don't know the condition of the battery. Well, let's plug that back in. And yep, back up to 6 volts again. So I think the charge circuit's probably working okay. So the next thing I want to check, am I getting the various DC supplies? So you've got VBAT coming in here, you've got a PNP transistor, and what I think this is doing, it's producing a supply that can kickstart the ASIC and also actually control this flyback circuit here. You can see the various control signals coming from the ASIC itself. At the end of the day, I should get a variety of DC voltages here, plus 3.3, plus 5, two more positive 3.3, a minus 3.3, and a minus 30 volts by the looks of it. So let's check that. I know I'm getting VBAT, but am I getting these other voltages here? Let's go down onto the circuit board and test them. Okay, and the first test point I'm going on to is the positive 3.3 GAR, and that's down here, and yep, I'm getting 3.3 volts there. So here's positive 3v3 GAR, that's the one I've got working. That's obviously coming from VBAT via this PNP transistor. The idea being it kickstarts the ASIC. Once it's up and running, then the supply, the 3.3 volt supply, will actually come from the flyback circuit back this way and power the ASIC directly. So I'm getting that supply there, no problem. However, I'm not getting any of the others, and that's probably because the unit's switched off. Okay, so here's what I've found out so far. So as I said earlier, you've got the power adapter coming in here, you've got the battery connected up here. The power ASIC itself is powered up all the time. And if the VBAT, the battery voltage, is within spec, then the power ASIC will send a signal out to the digital ASIC along here to tell it to turn on. So therefore, if the batteries are all within spec, both ASICs are powered up. And at the same time, of course, the flyback converter will be up and running to produce the various supplies in and around the circuit. So here's the signal here coming from the power ASIC, which basically tells the digital ASIC to start up. Now there is actually a watchdog IC here, and as long as the digital ASIC's powered up, it will pulse the watchdog input line here on that watchdog. And obviously if it stops pulsing for any reason, the digital ASIC's not working, then the ASIC will self-reset as output from the watchdog IC here. So I've measured the WDI, the watchdog input pin on the watchdog IC, and it's pulsing away quite correctly from the signal from the digital ASIC. So at the moment, I believe the digital ASIC is up and running. And there on the scope is actually the watchdog signals to that watchdog IC. And if I move on to pin 1 off camera, there is the reset and active low signal from the output of that watchdog IC. So everything's okay. The watchdog IC is working okay, and it looks like the digital ASIC is up and running. However, as I mentioned earlier, I don't seem to be getting any of the other voltages from that flyback converter. So jump forward a few minutes and I think I'm getting somewhere. So as I said, here is the signal VGR val from the power ASIC instructing the digital ASIC to power up. Comes in and interfaces with the watchdog circuit. I'm getting a nice watchdog signal into that watchdog IC. The reset pin is permanently high. That's good. However, this power on off output from the digital ASIC, which routes back to the power ASIC, isn't working. It's permanently low. Let me take you to that schematic. So here's that power off control coming back into the power ASIC, and when that line's high, the power ASIC then enables the flyback circuit, and you would get all these other voltages here. So what I did was I went ahead and tied TP528, the power ASIC side of that signal, to 3.3 volts directly. And when I do that, the flyback circuit powers up and I get all the correct DC voltages on the flyback circuit. So for some reason, this power off signal coming from the digital ASIC isn't working. Now, I'm not immediately going to jump the gun and think that the digital ASIC's got a partial fault with it, because there is actually a lot of other functionality coming in and out of that digital ASIC. So it's probably that this signal here is inhibited by some other problem round about the actual interface itself. Now, as you can see, it's a lot going on, so I'm just going to have to probably randomly go around and check things and have a look and see if I can find anything that's perhaps not working. And like I said, that is in turn inhibiting this power on-off signal back to the power ASIC. Well, step forward, another lot of troubleshooting, and believe it or not, I don't think I can repair this. I think it's knackered. And the reason I say that is because in the service guide which I've found, there is actually a truth table that you can follow to measure the various signals, some of which I've already been checking, like VGAR val, main val, and a few of them. And following this here, I've come to the conclusion that the flash ROM is not okay. Now, the reason I think the flash ROM's knackered is because in the service manual, it does actually give you a little procedure on how the unit switches on and the various operating modes. And number 3 here is, if the power adapter is connected, the power ASIC output main val will go high. I'm getting that. And the embedded digital ASIC program called the mask software starts up. The mask software then goes off and checks if there is valid software in the external flash ROM, and if not, test tool does not start up. And as I said earlier, the power ASIC instructs the digital ASIC to start up. There's VGAR val coming in, and the watchdog, like I said earlier, is up and running perfectly. The digital ASIC is actually working correctly. The main mask software inside the digital ASIC is actually running. But before it can instruct the device to power on via the power on off command back to the power ASIC, it's obviously going off and checking to see if there's valid software in the external flash ROM. And that is actually explained, exactly that procedure here in the service manual. So seeing as I'm not getting anything coming out of here, I did actually go ahead and pull that line high manually with a resistor, and I managed to get the power ASIC to start up and generate the external flyback converter and all the DC voltages, but I still wasn't getting nothing on the LCD or anything like that. And the reason for that is, I think the flash ROM's knackered. It's either that or there's some interface problem on the digital ASIC itself, whereby it's partially not working. But I would hedge my bets that the external flash ROM here is faulty. So there's not really much I can do about it at the moment. I am going to try and see if I can pick up another one of these units, maybe with a different fault in the future, and maybe I can transplant the flash ROM from it. Either that, or maybe there's a way I could download the flash ROM contents, the hex file from the Fluke website, something like that, but I highly doubt it. And maybe I could program a new one externally and solder it onto the board. Either way, for this video, maybe call it a part 1, but it's faulty and there's not much I can do with it at the moment. Thanks for watching.